When we're finding the factors of a polynomial, that is tied closely to finding the zeros of the polynomial. And so we'd like to be able to figure out how to do that. How can we find the zeros of a polynomial? And we have this test or this theorem here that's very powerful. We call it the rational zero test, or it's also called the rational zeros theorem. It says that if f is a polynomial with integer coefficients, and that's important, it has to be integer coefficients. We can't have fractions or decimals or crazy irrational numbers as our coefficients. Then the rational zeros of f are all of the form a factor of the constant term divided by a factor of the leading coefficient. So that means that if I'm looking at, for example, this polynomial here, if I want to find the rational zeros, meaning the zeros that can be written as fractions, that's what a rational number is, then we will take factors of the constant term, which is this 6 here, and the factors of 6 are positive and negative 1, positive and negative 2, positive and negative 3, and positive or negative 6. So those are all the numbers that go evenly into 6. And we divide by factors of the leading coefficient. Okay, the leading coefficient in this case is 1. So, well, the only factors of 1 are positive and negative 1. So this tells us that the rational zeros of this function here, the only possibilities, are when we take each of these numbers and divide them by positive or negative 1. Okay, that gives us a list of possible numbers. Now, of course, dividing by positive or negative 1 is just going to either keep the number or change the sign on it. So that just ends up giving us the list of positive or negative 1, positive or negative 2, positive or negative 3, and positive or negative 6. These are the only possible rational zeros of this polynomial. So now what we're going to do is we're going to start checking them to see if they are, which of these are zeros. Okay, so what we're going to do is just do a synthetic division. Okay, we'll set up our synthetic division with this polynomial. We set up our coefficients, 1, negative 1, 1, negative 3, and negative 6. And then we start to test numbers out here. Okay, and we don't really know which of these are going to work, so we just start with whatever we want. Okay, I like starting with positive numbers, I like starting with small numbers. So my positive 1, I like to start with there. We bring this 1 down and multiply. 1 times 1 is 1. We add and we get a 0. 0 times 1 is 0. 1 plus 0 is 1. 1 times 1 is 1. Negative 3 plus 1 is negative 2. And negative 2 times 1 is negative 2. And adding those, we get negative 8. Now, if we're trying to find that something's a 0, we're, of course, looking for a 0 in this last entry here. Okay. And we didn't get that, which means that 1 is not a 0 of this polynomial. So now we just go back and we try something else. Okay, I'm going to go ahead and try a negative 1. I like my small numbers. If we bring the 1 down, we get 1. 1 times negative 1 is negative 1. Negative 1 plus negative 1 is negative 2. Negative 2 times negative 1 is positive 2. 1 plus 2 is 3. 3 times negative 1 is negative 3. Negative 3 plus negative 3 is 6. And 6 times negative 1 is, this is negative 6. Negative 6 times negative 1 is a positive 6. And negative 6 plus 6 is 0. So right there, we have a 0. That tells us that negative 1 is a 0 of this function. Okay. Not only does it tell us that, it actually tells us a way to factor this polynomial. It factors as x plus 1, because if negative 1 is a 0, then x plus 1 is a factor. Notice that if you plug a negative 1 into this x, negative 1 plus 1 is 0. And it tells us that the other factor has these coefficients here. So that tells us that we have x cubed minus 2x squared plus 3x minus 6. Okay. Notice that the exponent on the x dropped from its original degree of 4 down to 3 because we pulled one of the x's out. So this process right here has shown us a factored form of our polynomial. But because of the fact that we know that polynomials will always factor down to linear or irreducible quadratics with real numbers, this we know will go further. Okay, so we want to be able to factor this even more. And what we can do is we can keep checking these numbers here. We can keep checking to see, to find more rational zeros. Now, when a number works as a 0, it might actually work again. It might have a higher multiplicity. And so I'm going to check it until it stops working. So -1 will we'll work off of these numbers here. Bring the 1 down. 1 times -1 is -1. -2 plus -1 is -3. -3 times -1 is 3. And 3 plus 3 is 6. And 6 times -1 is -6. And if we add those, we get -12. So we didn't get a 0 here. That tells us that -1 doesn't work again. Okay, so it's not a 0 of multiplicity 2. It's just a 0 of multiplicity 1. Okay. So now we move to our next number. We've tried positive and -1. Let's move on to 2. Let's try positive 2. We bring the 1 down. 1 times 2 is 2. -2 plus 2 is 0. 0 times 2 is 0. 3 plus 0 is 3. 3 times 2 is 6. And -6 plus 6 is 0. So that 0 right there tells us that we just found another 0. Okay, so we can continue to factor this down now. We have an x plus 1. And then since 2 is a 0, that means x minus 2 is a factor. And these coefficients here tell us what's left. Okay, we drop down in power one more. So from cubed, we go to squared. X squared plus 0x plus 3. Okay, so now we have a factored form. Notice we've got a linear factor here, x plus 1, another linear factor, x minus 2, and a quadratic factor, x squared plus 3. Now, x squared plus 3 is an irreducible quadratic. Okay, and that you can check just by, you can find its zeros using the quadratic formula, or just setting it equal to 0, and you'll find that its zeros are complex numbers. And so this is an irreducible quadratic because it doesn't have real zeros. Okay, so the only rational zeros of f are -1 and +2.